I'm going to go through some examples of partial derivative questions of the type that might come up in exams. So this is exercise sheet 6 and question 1. So we're given this function. Z is 5x log y minus 12x squared plus 2y to the power of 4. So z here is a function of x and y. And we're asked for all of the first and second partial derivatives. So first one, del z del x. So I differentiate that function with respect to x, treating y as a constant. So 5x log y becomes 5 log y. Minus 12x squared becomes minus 24x. And 2y to the power of 4 doesn't have any x's in it, so it becomes 0 when you differentiate with respect to x. Next, with respect to y, the derivative of log y with respect to y is 1 over y, and 5x here is just treated like a constant. So it's 5x times 1 over y. That minus 12x squared has no y's in it, so it goes to 0. 2y to the power of 4 becomes 2, that stays in front. That y to the power of 4, the power comes down and is reduced by 1. 4y cubed. So that's equal to 5x over y plus 8y cubed. Next, the second derivative with respect to x, del to z del x squared. That is, again with respect to x, partial derivative of del z del x. So that's equal to the derivative of del z del x was 5 log y minus 24x. So I differentiate 5 log y with respect to x while treating y as a constant. There are no x's in that, so it goes to 0. 24x just becomes 24, minus 24. So that's equal to minus 24. The second derivative with respect to y, well, that's just differentiate again with respect to y of the partial derivative with respect to y. That's del del y 5x over y plus 8y cubed. So we're treating y now as our variable that we differentiate with respect to, and we're treating x just as a constant. So 1 over y is y to the power of minus 1. So we have our 5x times minus 1 times y to the power of minus 2. So again, y was to the power of minus 1. So the minus 1 came out in front, and I take 1 off the power, and it goes down to minus 2. 8y cubed, well, that 8 is there, and then we have 3y squared. So that's equal to minus 5x over y squared plus 24y squared. That's the second partial derivative with respect to y. There's only one more to do, which is the mixed second partial derivative. So we can either take the derivative with respect to x first and then y, or y first and then x. So if I look at the two of them, well, they look about the same. So I'm actually going to do both, and you'll just see that they come out the same. But in reality, we only have to do one, because they will always be equal. So the mixed second derivative, del 2z del x del y, is the partial derivative with respect to x of the partial derivative with respect to y. So it's del del x of del z del y. So I'll pop in my del z del y that I got earlier, which is 5x over y plus 8y cubed, and I differentiate that with respect to x, treating y as a constant. So I have 5 times x over y. That just becomes 5 over y when I differentiate with respect to x, treating y as a constant. 8y cubed, there's no x's in it, so that goes to 0. So it's 5 over y. The other way I could have gotten this derivative is to go first with respect to x and then y. So that would be del del y of del z del x. So we got del z del x earlier. It's 5 times log y minus 24x. So I differentiate that now with respect to y, treating x as a constant. So the derivative of log y with respect to y is 1 over y. So that's 5 times 1 over y. 24x has no y's in it, so that goes to 0. So I'm left with 5 over y. And of course they're the same, no matter what way I do it. Question 2 gives me again z as a function of x and y. So I'll start off again with del z del x. So I differentiate that expression with respect to x while treating y as a constant. So xy squared just becomes y squared. Minus 11x squared becomes minus 22x. 8y cubed has no x's, so it goes to 0. And I have minus 5x times cosine of 2y. So that just has an x to the power of 1 in it and a bunch of constants. So it just becomes minus 5 cosine of 2y. So let's take out the 0, write it down. Next, I'll do del z del y. So now I'll differentiate with respect to y while treating x as a constant. So xy squared becomes 2xy. Minus 11x squared goes to 0. 8y cubed becomes 24y squared. And this 5x now is just a constant in front. Cosine of 2y becomes minus sine of 2y times the derivative of what's in the brackets, which is just 2 with respect to y. So I'll tidy that up. So that's the first partial derivatives. Let's do the second partial derivatives. Del 2z del x squared. So that is del x of del z del x, which is del x of, well, I got that above, it's y squared minus 22x minus 5 times cosine of 2y from above. So y squared has no x's in it, and remember now we're differentiating with respect to x, treating y as a constant. So I get 0 from y squared, I get minus 22, and that last term, minus 5 cos 2y, has no x's in it, so that goes to 0. So I get minus 22. What about the second derivative with respect to y? Well, that's del y of del z del y, which is del y of, I got del z del y above, 2xy plus 24y squared plus 10x times the sine of 2y. So now I'll differentiate that expression with respect to y, treating x as a constant. So 2xy becomes just 2x. 24y squared becomes 48y. 10x times sine of 2y. So that 10x is just a constant in front. Sine, if I differentiate sine, I get cosine. So I differentiate with respect to what's in the brackets and get cosine of 2y, and then multiply by what's inside the brackets and get 2 with the chain rule. So that is equal to 2x plus 48y plus 20x cosine of 2y. And there's one more partial derivative to get. So the one I will get is del 2z del y del x. So that's the derivative with respect to y of del z del x. This is the mixed second derivative. So del z del x from above is equal to y squared minus 22x minus 5 times the cosine of 2y. Well, that is equal to 2y. 22x goes to 0. We have that minus 5 in front, and it becomes cosine becomes minus sine of 2y times the derivative of what's in the brackets, which is 2. So I get 2y plus 10 times the sine of 2y. And just for one last check, I'll do it the other way. So the other way would be to go first with respect to y and then with respect to x. So that would be del x of del z del y, which we got above. It's 2xy plus 24y squared plus 10x times the sine of 2y. And if we differentiate that now with respect to x, treating y as a constant, that's what the del x means, we should get back the same thing we had above. So 2xy becomes 2y, which is good. 24y squared becomes 0. And 10 times x times sine of 2y differentiated with respect to x just becomes 10 times the sine of 2y. And so the mixed second derivative comes out the same no matter which way we do it, which it always will. Okay, in question 3, I'm given my expression for z as a function of x and y, and I go straight in again, get del z del x. So differentiating with respect to x, treating y as a constant. So I get 2x times y cubed from that first term, minus 12x to the power of 4 becomes minus 12 times 4 is 48 times x cubed. That goes to 0, 7y squared, and I get minus 4 times the sine of 3y. Because that 4 and that sine of 3y are all just constants now. And they're all times x to the power of 1, so I just get the constants left. Del z del y. Same thing again, but I differentiate with respect to y, treating x as a constant. So I have x squared times 3y squared. 12x squared becomes 0. I get 14 times y from 7y squared. And here my 4x is a constant, stays in front. Sine becomes cosine of 3y. And by the chain rule I multiply by the derivative of 3y, which is 3. So I have 3x squared y squared is 14y squared minus 12 times x times the cosine of 3y, where I've just multiplied that minus 4 by 3. The second derivative with respect to x, that's this thing, the derivative of z with respect to x and then again with respect to x, so that's equal to del x of my del z del x above, which is 2xy cubed minus 48 x cubed minus 4 times the sine of 3y. So that 2xy cubed becomes 2y cubed. 48x cubed becomes minus 48 times 3 times x squared, and there's no x's in that last term, so that just becomes 0. So I get 2y cubed. 48 times 3 is 144. And that's my second derivative with respect to x. What about with respect to y? Well, I'm going with respect to y and then again with respect to y. So if I pop in my del z del y that I got above, it's 3 times x squared times y squared plus 14 times y squared minus 12x times cosine of y, 3y. So now I differentiate that with respect to y, treating x as a constant. So that y squared becomes 2y. So I get 3x squared times 2y. 14y squared becomes 28y. And that minus 12x is a constant in front. Cosine becomes minus sine of 3y. And then by the chain rule I multiply by the derivative of what's in the brackets, which is 3. So I'll tidy all this up. That's 6x squared y plus 28y plus 12 times 3 is 36. It was plus 36x sine of 3y. And there's my second partial derivative with respect to y. Now let's do a mixed one. Let's do second derivative with respect to y first and then x. So that's del x of del z del y. So that's equal to del x, and I'll pop in my del z del y here. It's 3x squared y squared plus 14y squared minus 12x times the cosine of 3y. So I differentiate all that now with respect to x, treating y as a constant, i.e. get del x. So 3x squared y squared. So that x squared becomes 2x, and the rest is all just constants for now. 14y squared is like a constant with respect to x, so it becomes 0. And I have minus 12x times cosine of 3y. So everything apart from the x there is just a constant. So I have x times all that, so I end up with just actually minus 12 times the cosine of 3y. So I tidy that up and I get 6x y squared minus 12 times the cosine of 3y. And that's partial derivatives. That's all the partial derivatives, or at least all the first and second partial derivatives for that function. So there's really nothing to a question like this except to remember for each derivative that you take, what is your variable that you're differentiating with respect to and what you're keeping constant. And then it's just basic differentiation from there.